Okay, so we're actually finally going to get started proving things about computers. But of course, if we want to prove things about computers, the first thing we need to do is define what the heck a computer is. So the plan for this semester is we're going to start with a very, very simple computer and prove things about that computer, and then we'll move on to more complex computers over time. So our first simplest computer is going to be kind of a theoretical computer, and it's going to be a computer that can recognize a language. So let's just remember, right, a language is a set of strings, right? And an alphabet is a finite, very important, set of symbols. Okay? And we've also said that lambda is never an element of our alphabet. Okay? Lambda is a special symbol, but it represents the empty string, and we're just going to treat it as a string rather than a symbol. Okay? And so what's our first computer going to do? Well, our first computer is going to take a language and a string, and it's going to say one of two things. It's either going to give us a thumbs up, yep, this string is in this language, or nope, thumbs down, the string is not in this language. So, you may want to ask, could we actually use this computer for anything real? Is there any, okay, it's a theoretical computer. Okay, you're taking a theoretical computer science class. Maybe there's no use for it, but maybe there's something. So before you keep moving on with this video, see if you can think about what you might be able to use a computer that all it could do was tell you if a string was in a language. Well, one thing that it could do is it could recognize an integer, right? So it could tell us whether numbers are integers or not, and we could use that in, say, a Java compiler, right? Or in fact, there's a ton of stuff we could do with a Java compiler, right? Because we could take a look and recognize, we could kind of parse a line of code and decide whether it was syntactically correct, right? We could have a language of syntactically correct lines in Java. And in fact, compilers use sort of simulated computers like this a lot when you're actually designing a compiler. So here's our game plan for today. What we're going to do is I'm going to define this very, very simple kind of language, right? And I'm going to build that theoretical computer that recognizes this language. And we're going to learn to prove things about it. We're going to learn all sorts of different ways to represent computers that recognize this language. And we're going to do that for a while. We're going to do that for like a month and a half even. And once we've done that with the super simple computer that just recognizes this very, very small, specialized set of languages, then we'll move on to the harder languages. So the set of languages that our simple computer is going to recognize is a set of languages called the regular languages. We just call them the regular languages. So this comes straight out of your book. What we're going to do is we're going to use a inductive definition of what the regular languages are. So I'm going to tell you what the regular languages are by giving an inductive definition of the regular languages. So here's what we've got. The first thing I'm going to tell you is that the empty set, that's a regular language. So if anybody asks you, is the empty set a language, you already know it is because it's a set of strings, right? It happens to be an empty set of strings, but the empty set is still a set of strings, so it's a language. And now if somebody says, is the empty set a regular language, you can say yes, because the definition of regular languages tells you the empty set is a regular language over a particular alphabet. Okay. Another set that is just defined to be a regular language is the set whose only element is lambda, right? So a language where the only string is the empty string, yep, that is a regular language, okay? And finally, the third part in the base case, and these are like the simplest cases, is that if you have any symbol that's in your alphabet, the set that contains just that symbol is a regular language. So, for example, if my alphabet is the set A, B, C, then from these first three rules, we know about, let's see, 1, 2, 3, 4, 5 regular languages. So, empty set's a regular language. The set containing lambda is a regular language. The set containing just the symbol A, but that's the string A, right? A string made up of just one letter A. That's a regular language. So is the set containing just the string B. So is the set containing just the string C. Okay, so that's what we know from our base case. Let me clean that up and then we'll talk about the inductive step. Okay, now let's look at the inductive step. And the inductive step says, if you already have two regular languages, let's call them L and M, then these three other languages that you can build out of L and M are also regular languages. So if you have two individual regular languages, L and M, so for example, maybe we have the language A and the language B, and we're talking about, again, our alphabet for this example is going to be the set A, B, C, right? And we happen to have these two languages. We'll call that one the language L and that one the language M. This tells us that L union M is also a regular language. So what is L union M? Well, that would be the set containing these two strings, A and B. They do happen to be symbols, but in this case we're talking about a language. Language is a set of strings, so these are just strings of length 1. Okay. Another thing that the inductive step tells us is that ML, the two sets concatenated together, is a regular language over A. So this tells us that, let me change color, the set B, which is M, concatenated with the set A, and of course we could do it in the other order, but I'm doing M then L because that's what this line happens to say. Of course, we could of course change what we call L and what we call M. But it says this is a regular language, and what is this? Well, this is just the language where you take one thing from here and one thing from here. There is, in fact, only one thing in each of those, so that's the language containing a single string, BA. Okay? And finally, this tells us that L star is a regular language over A. Now, this is interesting because this tells us that we can have infinitely, we can have languages that are infinitely long. So, for example, if we just change color one more time, we know that this is a regular language, right? And this last rule here tells us that if we have a regular language, we can also star it, right? And in this case, that means that we get lambda, then A, triple A, and so on, right? And so this set here, well, that's a regular language. Okay, so this tells us what languages are regular, and it does it using using these pretty simple rules. Now, it probably would help you if you, when you're continuing watching this lecture, to just kind of have the book open to this page in chapter 11, just so you can see this for a little while. So, just to review, let's suppose my alphabet is just the set containing two symbols A and B. If you look at the base case, those three rules, what languages do we know that are regular over A? Well, we know there's 4 languages that are regular. There's one, the empty set. Another language is the language just containing lambda. Another language is the language just containing A. And another is the language just containing B. So the base case gives us a set of 4 different languages, right? Each of these is a set of strings. The inductive step gives us a bunch more languages, right? We can now take the union, we can concatenate, we can take the star. So for example, B star, which is, it's a lambda, doesn't look like a great lambda, but lambda, B, 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 and so on, is regular over A. We know we can concatenate, so AB is regular, but that also tells us that the set AB starred is regular, right? What's that? That's the set that starts with lambda, and then we have AB, and then we have AB, AB, and then we have AB, 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 and so on, right? So here I ask you a question. How big is the set of regular languages over A? And keep in mind, each language is a set, right? So here is one language, and that is a set. Here's another language, and oops, and that's a set. Here's another language that's a set, right? And I'm asking you, how many of these are there? How many languages are there that are regular languages over the alphabet A, right? And the answer is there's an infinite number of them, right? Because every time we have something, we can make something bigger using union and concatenation and star. So there's an infinite number of regular languages. Now, considering that I said that we're starting out with a very simple kind of language, these regular languages, it's very simple, but there's still a heck of a lot of them. So here's a question for you. Is this set a regular language? And think about it for a minute. Well, the first thing I've done is this slide is actually a little bit bogus, because I really should say, is it a regular language over the alphabet, and give you an alphabet, maybe over the alphabet ABC, right? Because if I don't tell you what my alphabet is, I can't tell you if it's a regular language. And the answer is yes, indeed it is. And here's why. The base case rule gives us that B is a regular language over this alphabet, right? And we can star this regular language, because we know that from the inductive step. And this thing starred is actually what we've got here, right? This is just B star. This is 0 or more times taking something out of here. So there's 0 times taking a string out of here. Here's just going through once and taking a letter. Here's taking 2 letters out of there, and so on. So, yep, this language here is indeed a regular language. This is saying let A be an alphabet, so A is now defined to be ABC, I'm sorry. And I want to prove that A comma BC is a language. Oh, well, is it a language? And I say prove it. Well, sure, it's a language, right? What's a language? A language is a set of strings, right? So I guess, how do I prove that? Let's see. A comma BC is a set of strings. So yeah, I guess it's a language. We're done. This one's a little bit more interesting here. Is it actually a regular language, and can we prove that? And the answer is absolutely, it's a regular language over the alphabet A. And to prove that, what we can do is we can build it up. So we can say, well, A is a regular language. Oops. Over the alphabet A, right? And B is a regular language, and these are all because of the, let's see if I can squish this ever so slightly smaller, hang on. Okay, and why is the set A a regular language over the alphabet A? Well, that's one of the base cases, definitions of regular languages. B is also a regular language over the alphabet A, same reason, base case. Let's give these numbers. That's line 1, that's line 2, that's line 3. C is a regular language over the alphabet A. Again, that's the base case. But that tells us that the set containing BC is a, these are supposed to be ditto marks, right? Is a regular language over the alphabet A. Why is that? Because we're doing, we took line 2 and line 3 and we used the concatenation rule, right? And so finally, the set containing A and BC is a regular language over the alphabet because we combined line 1 and line 4 and we used the union rule. So there are a couple of different ways we can specify a regular language. It is a language, so it's a set, so we can specify it using set notation like we've always done. But computer scientists always like shorthands, and one thing that I'm going to teach you now is kind of a shortcut. It's called a regular expression. And regular expressions are a way to represent regular languages. Really, we use them because they're just a little bit easier to write. We don't have quite so many curly braces and stuff. In fact, we don't have any curly braces, but we save a little bit of writing time. So somebody came up with this idea of the regular expression. If you've taken lab techniques or some other courses, you may have heard of regular expressions before. What I'm going to teach you is similar but not identical. Before we talk about regular expressions, I'm going to let you in on a big secret, okay? If you have a regular language, there is a way to represent it with a regular expression. Furthermore, if you have a regular expression, that represents some regular language. So you can go back and forth. If you have a regular language, you can turn it into a regular expression. And if you have a regular expression, you can turn it into a regular language. It actually represents a regular language. So this slide is very similar to the one we saw about regular languages. And you actually, as you look at it, I want you to refer to the page in the book that has the definition of regular languages, because you'll see that these are almost the same, right? Very, very similar. So in our definition of regular languages, we said that the empty set was a regular language. And we're also going to say that that same symbol, the empty set symbol, which is a little bit weird, but we'll just, for this one thing, we're going to use sets, nowhere else. The empty set symbol, it's also a regular expression. So in regular languages, we talked about the empty set as a set. Here we're just using this as kind of a symbol. Here we say that lambda by itself is a regular expression. Well, that's actually going to correspond, I'm kind of giving you a sneak preview here. That's going to correspond to this language. The language just has lambda. And I'm sure you're figuring it out by now. The symbol A by itself is a regular expression, and that's actually going to correspond to the language which just has an A in it, right? And when we talk about regular expressions, if you already have two regular expressions, say one of them is called R and the other one's called S, then you can build up more regular expressions out of that, just like if you had a regular language in the previous definition of regular languages, you could build up bigger and bigger regular languages from smaller ones. You can build up bigger and bigger regular expressions from smaller ones. So this first one here, the R with parentheses is a regular expression. That's kind of a new extra because sometimes we need to parenthesize things now. Here we say R plus S is a regular expression over A. And I'm going to tell you that in the language world, that corresponds to union. So L union M, if we talk about L and M being languages, being regular language, then L union M is also a regular language, right? If L and M individually are regular languages, we can take the union of those two languages, and that's what this plus is, right? It's plus is kind of corresponding to union. And one way that I tell my in-person class to remember this, which is completely hokey, but if you're watching the video, you might get it. You might like it, is if I draw a plus sign, right? And then I kind of try and make it a little bit 3D. Does that look the least bit 3D? No, not to you, I know. Let's see, maybe we'll make it have some width and then we'll make it 3D. All right, the iPad is not the best for making something look 3D, right? But if you look at this, don't you almost, if you squint, see the letter U in there, right? And that U is union. So remember, I know, totally bogus, but probably you will remember because Dr. K did this ridiculous thing with the plus and the U thing. So just remember, if you have a regular expression, we use plus, whereas in languages with sets, we use union. Try and remember that plus corresponds to union. We'll see this again in a minute. We also have this dot. That dot's going to turn out to be our concatenation, so where we had our ML before. And our star, well, we're using the star again, so that'll be like M star. And then, like I said, there's this one extra piece of inductive step, which is you can put parentheses on. And that's just to help us do order of precedence, or order of operations. So all the stuff that I just erased that was down here, that's useful and interesting. It tells us kind of how to move between regular languages and regular expressions. But truth be told, you don't actually need to know that right this second. You'll need to know it in like 5 slides, so it's useful to show you it now. But remember that the basic thing that this slide is telling us is what is a valid regular expression. Okay? How do you know if an expression is a valid regular expression? So here's an alphabet. And now we're being asked to list some regular expressions over that alphabet. So we could take all our base cases. The empty set's a regular expression because it told us that on the previous slide. Lambda is a regular expression. Note there's no braces here. This is just lambda. We're talking regular expressions, they're not regular languages. A is a regular expression by itself. B is a regular expression by itself. And we can build up really complicated ones like A star, AB plus A plus B star, and so on. That's a regular expression. If you go back and look at the previous page, you'll see that I can build this up using my plus and my parentheses and my star and stuff. Now, it seems to be a never-ending theme in this class that computer scientists and mathematicians, this is actually sort of a mathematical class, and a mathematical topic too, get lazy, right? And so we have this funky dot that we use that I told you is part of a regular expression. And we're going to stop writing it. Just like if you think of the dot as times in math, people stop writing it very quickly. If they say A times B, they don't write A dot B. They just write AB. And when they're talking about A dot B dot C plus C dot B, they just write ABC plus CB. And we're going to do exactly the same thing here. We're going to leave out the dots. And remember, the dot represents concatenation. We'll get there in a minute. But really, you can kind of do the same thing. It works very similar to the way, well, identical really, to the way mathematical plus and times works. So you can kind of shrink these down. And in fact, I just realized that I did that on the previous slide, right? With my, my regular expression that I gave you, I didn't put any dots in. I just got rid of them and left it like this. And of course, just like with math, we can talk about precedence rules so that we can get rid of a lot of the parentheses if we want. I usually put in parentheses if I'm doing anything complicated, but you can get rid of the parentheses. So here's kind of the reverse question. I said add parentheses and dots to the following regular expression to show order of evaluation. So let me just write it out a little bit bigger. So we've got A plus, and I know that there's going to be dots in there, B dot A star, right? And if we look at this, star has the tightest binding, so this A is going to get starred. That A star is going to happen before anything else. And then dot happens, so then we would do that. And finally, we would evaluate the plus. Keeping in mind, of course, that plus means union, right? And finally, here's the slide where I really tell you, I've told you this already, I couldn't hold back because it's just too darned obvious when you look at these. But let's just talk about the relationship between regular expressions and regular languages. So what we're going to do is we're going to talk about having some regular expression, maybe it's called E, and we're going to associate it with a regular language. So we'll talk about the language of E, or we'll write L of E. So we will start with a regular expression, like maybe we'll have the regular expression A, and we'll talk about the language of A. What's the language that corresponds to the regular expression A? Well, that is in fact the set containing just A. But you don't know that yet because we got to go to the next slide. So formally, here's the procedure. If you have a regular expression, and if your regular expression happens to be the empty set, then well, the language of that regular expression is just the empty set. If your regular expression is lambda, then the language of this regular expression, that's the set containing lambda. Okay? If you have a particular symbol A that's in your alphabet, the language of that symbol, you got it, right? The set containing that symbol. If you happen to have two regular expressions that you add together, what's the language of those two regular expressions added together? Well, it's the union of whatever language you get by just looking at the individual pieces, right? And this is where I said plus corresponds to union. Similarly, I said dot corresponds to concatenation. If you have two regular expressions that are dotted, you can translate the language of the dot of those two just by taking the language of the first one and concatenating it with the language of the second, right? And similarly, the star, the language of something starred, is just whatever you get, taking the language on its own and starring it. So here's three problems. It says find a language, that is a set of strings, to describe each of the following regular expressions. So let's see. Let me make this just a little bit bigger so we have some space. So the first regular expression that we have is this A plus BC. Keeping in mind that plus is union, this corresponds to the set A unioned with the set containing a single string BC. Or another way to write this is just A comma BC. Let's change color. This next one here, AB star plus C. Remember, star binds more tightly than dot or plus. This is saying take the language A, concatenate it with the language B starred, right? And union that with the set containing just C. So what does that mean? That means there's two types of strings in this language. The first is just the string C. And the second is an A followed by 0 or more B's. And let's do this last one here. This says 0 or more A's followed by the set containing B followed by 0 or more C's, so that's A starred concatenated with the set that just has a B in it, concatenated with C star. You can see why we developed these regular expressions, because writing this out is pretty nasty. And we're going to take that whole thing and we're going to union it with the set that just has one string, AC. Now, if you want, we can write the second two sets just a little bit more cleanly. Or maybe I shouldn't say cleanly. This is quite clean, actually, but in a way that may make it easier for you to understand. This first set is, let's see, you have an A, and then an A with one B, and then an A with two B's, and then an A with three B's, and so on, unioned with language C. And this next one, the purple one, it gets pretty rough pretty quickly. And what I want you to do is I want you to have a logical order that you specify these strings in. Okay? So the logical order that I find the easiest to use is length of string. So I say, so we're going to do something union the string AC. But to represent this piece, look at it and say, are there any strings of length 0 in this concatenation? And the answer is no, because we always have a B. So I'll start with just a B. And then I'm going to list all the strings that are of length 2. So I guess there's an A followed by a B, where we take 0 C's, or 0 A's, but we have a BC. And then let's talk about all the strings that are of length 3. So let's see, we could have an A and a B and a C, or we could have 2 A's and a B, or a B and 2 C's, and I guess I better dot 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 it at this point, union with that AC. Let's do an example the other way now. We've got a language and we want to have a regular expression that describes it. So this first problem here, part B, has just 3 strings, right? We have the string AA, the string AB, and the string AC. And so this is a language that just has 3 strings. It's made up of just 3 strings. And there's a couple of different ways we can represent that. We could just have the 3 strings plussed together for a regular expression. Or in fact, we could represent it like this, where we sort of simplify it a little bit. So now take a look at this one. What do you see? We've got a single A, and then we have 3, and then we have 5, and it says A to the 2n plus 1. And I guess really this should say, you know, somewhere in here, it should say such that n is an element of the natural numbers. So we've got 1A, we've got 3, we've got 5. Think about, how do you represent that? And here's your answer. It's a nice little regular expression, right? Basically, what I'm saying here is you definitely have 1A, and then you have 0 or more copies of 2 A's in a row. So if you have an A with 0 copies of this, that's just this A. If you have an A with 1 copy, that's this guy. An A with 2 double A's, this one, and so on. So here's an interesting language. Let's see, what have we got here. We've got lambda, and then it looks like all strings of length 1 made up just of A, B, or C, all strings of length 2 made up of just A's, B's, and C's, all strings of length n made up of just A's, B's, and C's, and I suppose really, again, I should say such that n is an element of the natural numbers. So can you think of what's the regular expression that corresponds to this particular language? I'll give you a hint, and I'll say that this language that we have here is exactly the same as this one, unioned with this one, unioned with this one. And before, oops, that should be 2 C's, 3 C's, and so on. Before you keep going, pause the video, convince yourself that I'm right here. And hopefully you convinced yourself that I was right, and maybe you even saw that that was just, you know, this A star corresponds to the set A starred, union with the set B starred, union with the set C starred. So now it's getting even more interesting. What have we got here? We've got find a regular expression that describes the language. So what do we got here? We have A to the 2k. So what is that? Let's just make sure we know. So that would be, I guess if k is 0, that would be lambda. And if k is 1, that would be AA. And if k is 2, that would be 4. And we're unioning that with this piece, which is b to the 2k plus 1. So we're unioning it with odd numbers of b's. So 1b, 3 B's, no lambda here, right? 5, 3, 4, 5, and some dot, dot, dots, and a closed curly brace. So how do we turn that into a regular expression, right? And in fact, before I make that change, let me ask you a question. I used K in both of these equations. And my question is, could I use different letters? Could I use say a Q over here and an R over here? So you may want to pause and think about it for a minute before I give you the answer. The answer is absolutely, because these are two distinct sets. So in this set it says, it's kind of like local variables in Java, right? This K is only in scope over this set. And this K here is only in scope in this set. So if we changed, say, this K to an R and that one to an R, then it would mean exactly the same. There's nothing here that says that there's some relationship between the number of A's and the number of B's. This is all of those strings that have an even number of A's, and this is all of those strings that have an odd number of B's. So here you go. Strings with an even number of A's, well, it is 0 or more copies of two A's together. Strings with an odd number of B's, well, you start with one B no matter what, and then you add as many more pairs from 0 up to as big as you like of double B's, and you end up with an odd number of B's. And of course we've got the plus sign in here because we're taking the union. Now here's a fun one. This says we want to find a regular expression for the language over the alphabet AB, and it's a language of all strings whose length is a multiple of 3. So here's one way to do it. What I did is I listed all the strings of length 3 that exist over the alphabet AB. And then I said, now take 0 or more of these. And I said that by taking a star. And notice that every time we go in here, we can take a different number of them. So let me just clean this. So, for example, the string AAA, ABBBAA, this long string, is in this language. Because what I did is the first time I took a string out of here, I took AAA. Second time I came in, I picked a different one. I picked ABB. And the next time I came in, I picked BBA. Right? And so you can pick as many, you can go in here as many times as you want and pick as many strings. That's the magic of the star. And you can pick a different string each time. Now, let me clean this up just one more time, because now I'll show you something kind of sneaky. This is certainly, this regular expression we have here is definitely all strings whose length is a multiple of 3. But so is this one, and this is kind of sweet. This says you have to pick an A or B and concatenate that with picking another A or B, and concatenate that with picking another A or B. So this little inner piece gives us 3 letters in a row, and it can be any 3 letters in any order over the alphabet AB. And then we have this star out here which says now take 0 more copies of it. So this regular expression up here, perfectly acceptable. This regular expression down here, that I'll clean up so you can look at it again. It's just a very sweet, neat way to write it. Okay, last one. This one is pretty tricky. It says strings with an odd number of A's. And this is really hard to come up with on your own. If you try, you should pause and try and see if you can do this, but don't be discouraged if you can't at first. This is one of those things where you see it done, you see a couple of examples, and then this kind of thing gets a little bit easier to do. So here you go. Here's the answer. Let me expand it a bit so that you can really see what's going on here. Strings with an odd number of A's. So what is this expression telling me? It's saying start out with 0 or more B's, as many B's as you want, right? Because we don't care about the number of B's. Have to have some A's, but we're going to start out with B's. After that, put an A. And after that, as many more B's as you want. So right now, just this first piece, if I look at that first piece, what I've got here, let me get rid of that little circling a little bit again. If I just look at this first piece here, I've got all strings that have one A in them, right? And they could have 0 or more B's, and the B's can be in front and the B's can be behind. Right? So I start out with a single A. And then the second piece, this is very clever because I say, now take as many more of these things as you like, because I've got this star here around the whole parenthesized piece. And this thing says, start with a B, then have an A, right? Start with 0 or more B's, then stuff an A in. Start with, have another 0 or more B's, then stuff an A in. Then another 0 or more B's in here. So the whole idea here is we definitely have 2 A's. If you're going to put in 1 A, you got to put in 2. And you can put in as many B's all over the place as you want. So let me just clean that up for you. And you can take a look at it again. Strings with an odd number of A's. So it's strings that have at least 1 A. You have to have 1 A there. And then 0 or more extra bits in there with at least 2 A's each time so that we stay odd.